All right, this video is not what I had originally intended. I was hoping to be able to do this live, but my internet is being incredibly flaky, so we're forced into this. So we're going to continue the discussion of dynamic programming, or DP, and so I'll occasionally call it dynamic programming, but as much as I can, I'll call it just DP, because I think the term dynamic programming is actually very misleading in a computer science context. So programming, and maybe if I write dynamic programming, I'll try to put it in quotes just to convey the idea that this isn't what it sounds like. Like when I say the words dynamic programming, it sounds like what I'm trying to say is that like the program updates itself as it goes or something like that. And it's not like that. Like that's not really what we're doing. We're not talking about like self-writing code or something like that. I know at least that was my first impression when I first heard the term dynamic programming back in graduate school. So we'll typically just refer to this as DP. And the thing that makes DP, aside from its connection to optimal control and rocket science in like the 1950s, is these two kind of bullet points. So here's our core concepts. And so anytime we do a new DP algorithm, we'll identify how these core concepts fit in the context of what we're doing. So the first concept is what we call overlapping subproblems. Overlapping subproblems. And so we saw this with the routing example last time, where we had this big network that we had to find a shortest path across, or a minimum cost path. And in that problem, the way it worked was we had a bunch of edges, and you had to pick edges that had low cost. And what we discovered as we started thinking about what an optimal path looked like is basically that each optimal path contained a whole bunch of other optimal paths for a subproblem. In particular, for the subproblem where you stop after a certain number of stages, right? So if there's n stages, then the length n optimal path contains a length n minus 1 optimal path, which contains a length n minus 2 optimal path, and so on. And so if we exploited that notion of overlapping subproblems, we could save ourselves having to regenerate a bunch of paths that overlap each other, right? And would each contain all this a bunch of similar information. And we were able to, in the context of that routing problem, we were able to take an algorithm that would have been an exponential time algorithm and cut it down to just quadratic time, okay, which was nice. And so the way we think about overlapping subproblems is that the solution to the overall problem, so I can call this the overall solution, or solution to the overall problem, is built up of solutions to smaller problems. So overall solution is, hold on a moment, turn off draw with touch there. Overall solution is built from solutions to subproblems. So what do we do with this? Well, we do with this something in the second bullet point, where we carefully choose which of the subproblems need to be solved, go solve them, and as they are solved, we record their solutions in some kind of a table. So here we carefully choose the right subproblems to solve, right? We go choose which ones, we go solve them, and then we record those solutions in a table. So comma, and then record sub-solutions, sub-problem solutions. Okay, and so this idea that we've got sub-problems that we need to solve puts us in a recursive context most of the time. So there's usually going to be some notion of recursion here, even if the notion of recursion doesn't make it into our final algorithm. So we'll have lots of DP algorithms that are not actually recursive algorithms, right? They don't involve calls to themselves, but they are still kind of founded upon a recursive idea. So one of the kind of the core canonical super simple problems that people a lot of times start with is computing Fibonacci numbers. So I don't recall if we've done this yet in this class or not. Yeah, I'm not sure. We may have early on at some point. But there's this sequence of numbers called the Fibonacci sequence. And it's defined like this. So it's a sequence of numbers, which means that it has some starting point, but then it's an infinitely long set of numbers that grows without bound or without limit. Neither of those were mathematically precise, but you know what I mean. So Fibonacci sequence is defined like this. So I'm going to define f1 as 0, f2 as 1. Okay, so I have these two starting point numbers. Let me make my pen a little bit thicker. So f1 is 0, f2 is 1. And then every subsequent number is the sum of the previous two. Okay, so fk is defined as fk minus 1 plus fk minus 2. All right, so what is f? I've got f1 and f2 defined. Now what is f3? Well, f3 is 0 plus 1, which is 1. Right, and so this is 0 plus 1. f1 plus f2 equals f3. And then once I have f3 defined, I can define f4. So f4 then is 2, which is 1 plus 1. See if this matches how I've got it written on my page. Yep, I've got my indexing right. It depends on whether you 0 index this or 1 index it, how you come out. F5 then is 3, which is equal to 1 plus 2. F6 is 5, and then the sequence continues. And there's a lot of really interesting, strange properties about this sequence. And in fact, when I was a kid, this was one of the first things that really got me excited about math, was all the weird connections that you run into with the Fibonacci sequence and some other concepts in math. But here's the idea of the Fibonacci sequence. Now, suppose we had some interest, like I did as a child, right? And when I was first getting into math, suppose we had some interest in identifying the nth Fibonacci number. So if our algorithmic question is, what is the nth Fibonacci number? We could think about various algorithmic approaches for finding that. So what is Fn, right? Or what algorithm would allow us to determine Fn? And so here's one idea, right? One possible answer is a recursive algorithm. And why would we come up with a recursive algorithm to find the answer to this? Well, because the sequence is defined recursively. So if we write a recursion that just implements this recursive definition of the Fibonacci sequence, then it should find us the nth Fibonacci number. Right? That shouldn't be a problem. So here's one that does such a thing. So let me call this algorithm fib recursive. Okay, so my algorithm fib rec. Okay, and it takes in a number n. And what is it trying to do? It's trying to find the nth. Well, we've got it written up there. Find Fn. Right? Find the nth Fibonacci number. Okay, so we need some base cases. So our base cases are given to us here by the definition of the sequence. So if f1 is 1, or if n is 1, then we should just return 0. So if n equals 1, right, if we're asking for the first Fibonacci number, then we just return 0. If n is 2, then we return 1. And otherwise, what do? We return the following. We return fibrec evaluated on n minus 1 added to fibrec evaluated on c n minus 2. Okay, and this should work. If I plug in, say I plug in 5, then what is it going to do? Well, it's gonna say, well, neither base case fires, So it'll go compute the Fibonacci, the fourth Fibonacci number with that first recursive call, and the third Fibonacci number with the second recursive call. And each of those will go and compute the things they need to solve the overall problem, right? To be able to identify the answer. And since all we're doing is we're subtracting 1 or 2 at each time step, at each recursion, we're guaranteed, as long as someone passes in an integer, we're guaranteed to land on either 1 or 2, right? As long as n is an integer that's greater than 1, this algorithm is going to be guaranteed to terminate. Okay, so let's think a little bit about what this algorithm would do. And the first thing we could do is we could just write a recurrence relation for it, right? So what's our recurrence relation? And in particular, let's think about the sum as the basic operation. So there's our basic operation. So the recurrence relation is going to be, it's going to look kind of deceptively simple. It's going to say to compute, as long as n is not 1 or 2, to compute the nth Fibonacci number, we do n addition, right? Well, there's just one addition in the pseudocode that I've written here. So there's a 1. And then we go do however many additions we need to compute the n minus 1th Fibonacci number. And then however many additions we need to compute the n minus 2th Fibonacci number. Okay, so there's our recurrence relation. Now, this turns out to be considerably more difficult to solve than it looks, right? So I highly encourage you, pause this video, try to work this thing out, try to use the reverse substitution method that we've done with the other ones to figure out what this recurrence relation is, and you'll find that it's not trivial. You'll have a very difficult time coming up with a generalizable way to send this thing all the way down to its base cases. Nonetheless, we can at least think about what the complexity might be, right? So we're not gonna, like, we haven't used tools in this class that we can actually solve this thing completely, but we can think about what it would do. And so just as a hint, if you are interested in solving this kind of recurrence relation, there's a method called the characteristic equation method. Characteristic equation, which would make it easy. Method, which you could use to solve this thing. And essentially, you end up characterizing these solutions to this thing as roots to a related polynomial. Okay, and this one happens to have a polynomial that is not too difficult to factor. All right, so that's that. But let's think about what would happen. So in particular, let's think a little bit about what this thing would do if we just plugged in 6. Okay, so what is t of 6? So explore t of 6. Well, we've got t of 6 here. So let's draw this as a tree. Okay, so when the algorithm gets 6 as its argument, it says I have to go find some answers to other problems, find some other Fibonacci numbers to get the answer to this one. So let me go do that. All right, so let me go solve t of 5 and t of 4. So where did those come from? Well, they came from up here, right? If I pass in 6 right here, then this is 5 and this is 4, right? And 6 minus 1 is 5, 6 minus 2 is 4. All right, so it has to go solve those. Now we can just continue this tree all the way down. So if I'm here at t of 5, what do I have to solve to solve t of 5? Well, I've got to solve t of 4 and t of 3, right? And n minus 1, n minus 2, where now n is 5. And I get the same thing over here. This would take us down to t of 3 and t of 2. Okay, and I'm just drawing, you might already be noticing some issues, but notice I'm just drawing the recursion tree as defined by the algorithm as we wrote it. That's it. I'm not doing any optimizations of any kind. Okay, so t of 4 now, t of 4 takes us down to t of 3, t and t of 2, T of 3 takes us down to T of 2 and T of 1. Okay, so now notice that these are leaves, right? That's a base case, that's a base case. Oh, that shows up beautifully. That's a base case, that's a base case. All right, my T of 3 here does what the other T of 3 did. It took us to a T of 2 and a T of 1. Those are all done. And then this T of 3 takes us to a T of 2 and a T of 1. Okay. And so now, every single one of these has found a base case. Okay. So now let's think a little bit about how many total additions we have done. So at each time this thing branches, basically, we have an addition. So we've got 1, 2, 3, 4, 5, 6, 7 total additions. Okay, so what is T of 6? T of 6 is 7. Equals 7 additions. Why does an addition give us a branch, or why does a branch give us an addition? Because a branch is literally this right here, right? This is a branch of recursion tree. Okay, so we've got 7 additions. Now what would T of 7 be? Let's think about what T of 7 would give us if I did that. Well, T of 7 would be equal to T of 6 plus T of 5. And I know T of 6. T of 6 is 7. I just computed it. And I actually know T of 5 also, right? T of 5 is, again, it's 1, 2, 3, 4. So T of 5 is 4. So if I asked for T of 7, based on this, I would actually get 7 plus, what did I say, 4, right, which is 11. Now, what would happen if I asked for T of 8? Well, that's equal to T of 7 plus T of 6. Well, that's interesting, right? So now that's going to be 11 plus 7, which is 18. And now notice this thing is growing pretty fast. The number of additions we have to make is going up pretty quickly, right? Going from 6 to 8 takes us from 7 additions to 18 additions. And there's no sign of this thing stopping. Also notice, just as a curiosity, notice that T of 8 equals T of 7 plus T of 6. And so it's almost like the number of additions also satisfies something that looks a little bit like a Fibonacci sequence, just as a curiosity. All right, so what's wrong with this? Okay, so what's the issue here? What is making this algorithm slow? Well, notice that we have T of 1. We have T of 1 circled 3 different times. Okay. Now T of 1 doesn't involve an addition, so that just by itself isn't giving us more additions. But it's interesting that it appears on many different leaves of the tree. Now, when does T of 1 appear as a leaf on the tree? Well, it appears when it gets called by T of 3. Well, where does T of 3 appear? So here's T of 3. Here's T of 3. Here's T of 3. So what do each of those T of 3s mean? Well, each one means an instance where the algorithm has computed the third Fibonacci number. Okay, so each T of 3 is a computation of F3, right? Which we do now. We do 3 times. So is there any reason to compute F3 3 times? No. What we should have done, right, in this algorithm is when we first found T of 3, when we first had someone ask us, or had some recursive call ask us, what is f of 3, it should have said, well, let's go compute that, and then let's put a pin in this that tells future versions of this algorithm not to compute f of 3 again. Like, let's save the answer we get. And so this is where we kind of connect to a DP idea in the Fibonacci sequence. Is that if we do this naively, if we implement the recursion naively, we end up recomputing a whole bunch of sub-solutions to the problem over and over again, right? We compute F3 3 times, we compute F4 twice, but then the bigger this tree gets, the larger those numbers go. So notice that if we had a T of 7, then we would be computing F3 not 3 times but 5 times, right? That would go up considerably. And so this is something that we should have in the back of our mind, right? We should have the idea in our head that we need to avoid doing extra work, right? That's what it means to be a good algorithm designer, is don't do the same thing twice, which means that when we identify a Fibonacci number, we should write it down and then not recompute it. Okay, so now how could we do better? Oh, and by the way, it's worth mentioning that T of n for this is exponential, right? So it's actually big theta of 1.618 to the n, right? Where this 1.618 is the golden ratio. So for any of you who care about such esoteric mathematical things, the golden ratio is this interesting quantity that shows up in a lot of places. It has some tight connections to the Fibonacci sequence, and it also happens to describe the complexity class of this particular algorithm. Right, so I hope that it's obvious what we should have done. Hope it's obvious that this is a bad algorithm, and that the right thing to do would be to start at 1 and work our way up. And if you start at 1 and work your way up, then you compute each Fibonacci number exactly 1 time, and you don't end up repeating all this work. Okay, so let's just finish this one out, and let's write the correct algorithm. I'll call it algo fib dp of n. And what we do is we save the solutions as we go. So we initialize an array f, from 0 up to n. We initialize f0, which will represent the first Fibonacci number. So f0 will be 0. F1 will be 1. Oh, I missed n minus 1. Okay, because there only needs to be n slots in this array. And then we'll just set up a for loop that says, starting at 2, so from I equals 2 to n minus 1, just assume that everything up to where I am, everything up to I minus 1 has been computed, and then use that to compute the next one, right? This is super simple stuff. Just set fi to be equal to fi minus 1 plus fi minus 2. Okay, and then at the end we return the last one. We return fn minus 1. Okay, and so this is almost not a DP algorithm because it's so simple, but it's kind of useful to introduce the concept in an algorithmic sense. What we've done is we've said, what are the interesting subproblems we need to solve? Well, we need to solve all of them. We need to solve each one of these subproblems, but we need to make sure we only solve each one once. And so the way to guarantee that we only solve each one once is we start at the first Fibonacci number, and then the second one, and then we just compute them all the way on up to the top, and then return the last one. Okay, and so this f is something that I'll often call a DP table. So this is my DP table. Okay, and so in my routing algorithm that I did last time, the DP table was represented by this idea of writing the optimal cost to go on each of the nodes. Right, as we went through the graph, on each node we wrote down what's the optimal solution from here, or what's the value of the optimal solution from here, and how do you build it, and so that storing information as we went was the DP table, right? So the DP table stores solutions to subproblems as we solve them. Of subproblems as they are solved.